or equivalent. That is, okay. So I'll assume that you guys are familiar with basic matrix analysis like transpose and determinants and rank of a matrix, all that. So these two lectures, O1 and O2, I'll brush over all those things, but there will be enough things that you are not familiar with in these two. But these first two lectures will be a little hot, and then you'll see that it'll become easier. Okay, so let's begin with review of vectors and matrices. Outline, these are what we'll do: basic properties, then vector norms, matrix norms, inner product, block matrices, gradient and Hessian. And like I said, since this is a review, it's not really a review because these things are something you probably didn't do in undergraduate unless you've taken 540. But at least this is high school level stuff, multiplication, determinants, inverse rank, etc. So that's why I'll breeze through these. Okay, so basic properties. Inverse of a square matrix. A square matrix has an inverse. A square matrix is a matrix with the same number of rows and columns. So A inverse A equals A inverse equals I. I is the identity matrix. It's a square matrix with all elements 0 except the diagonal elements, which are 1. AB inverse is B inverse A inverse. Remember this, don't ever make the mistake that AB inverse is A inverse B inverse. No, AB inverse is B inverse A inverse. Determinant of a square matrix. I'll use both these notations. Det AB is the determinant of the product AB, or I can use this notation. Anyway, so the determinant, are you able to look at the cursor? Yes. So the determinant of the product of two matrices is equal to the product of their determinants. The determinant of a transpose of a matrix is equal to the determinant of the matrix. Now, if alpha is a scalar, then the determinant of alpha A is alpha to the n times the determinant of A, where n is the dimensionality of this matrix. So A is a n by n matrix. It has n rows and n columns. So that's why this is alpha to the n. The determinant of A inverse is 1 over the determinant of A. Determinant of I plus AB transpose is equal to 1 plus A transpose B. Okay, a little bit about the notation here. Most of the time, practically all the time in this course, I'll use uppercase bold for matrices, lowercase bold for vectors, and italics, lowercase, or sometimes uppercase, italics for scalars. Okay, and furthermore, a vector by default, unless I specify that it's a row vector, every vector is a column vector. Okay, it'll have just one column. And so if A is a column vector, B is also a column vector, B transpose is a row vector. So AB transpose is a matrix. Okay, AB transpose is a matrix. So I plus AB transpose is also a matrix. Remember that the dimensions have to match, otherwise you cannot add matrices. Now on this side, 1 of course is a scalar. A transpose B is a scalar. It's also called the inner product of A and B. AB transpose is called the outer product of A and B. So AB transpose is a matrix, but A transpose B is a scalar. Okay. Okay. Conjugate transpose or Hermitian. So the Hermitian of a matrix A is equal to A conjugate transpose. It means all the elements of that matrix, I'm taking the complex conjugates, and then I'm doing the transpose. Most of this course, we'll be dealing with real matrices. AB transpose is B transpose A transpose. You have to flip the order of the two matrices. Same with, if you take the conjugate transpose, you do the same thing. AB, the Hermitian of that is B Hermitian, A Hermitian. A Hermitian matrix is one if A, its conjugate transpose, equals the matrix itself, then it's a Hermitian matrix. Now, for real matrices, A transpose equals A implies it's a symmetric matrix. Trace of a square matrix is the sum of its diagonal elements. So this matrix A, its scalar elements are A and then two indexes. This is the row index and this is the column index. Okay, so this is kth row, kth column. So these are the diagonal elements, kk. So the sum of the diagonal elements is the trace of the matrix. Trace of AB equals trace of BA. A transpose A is the trace of AA transpose. AA transpose is a matrix. A transpose A is a scalar. This is an important expression, the Woodbury formula. And there's another similar formula, the Sherman-Morrison formula. And now let's try to prove this so that you get an idea of how to deal with matrices, vectors and matrices. We have to prove this. Prove that A plus BC transpose inverse is A inverse minus A inverse BC transpose A inverse divided by 1 plus C transpose A inverse B. Now, why do we have a denominator? Remember, you can never divide anything by a matrix or a vector. Okay? Never ever do that. That's a fundamental mistake. So why do we have this denominator here is because this actually is a scalar. C transpose A inverse B is a scalar. Okay. So let's see how to prove this. I pre-multiply both sides by A plus BC transpose. So on this side, I'll get identity matrix, right? So this is the right-hand side. Right-hand side is equal to this. And then I open up this parenthesis. I get A plus BC transpose times A inverse negative A plus BC transpose times this whole thing. And then what I do is I'll again open it up, this and this. And so this is what I get. This I open up, I get AA inverse plus BC transpose A inverse minus this whole thing. What's AA inverse?
Identity.
It's the identity matrix, correct? So everything else I expect to cancel out to 0, right? Because on this side I have, since I pre-multiplied both sides with A plus BC transpose, I'm expecting an an identity matrix. And this gives me the identity matrix, so everything else has to be equal to 0, correct? Yeah. And so now let's try to simplify it further, keeping in mind the denominator, okay? And we know that the denominator is a scalar. The denominator has to be a scalar. Okay, so I open up this parenthesis and I get this. Now, see, okay, so this is what I have. I plus BC transpose A inverse minus this whole thing. Okay, I open up the parenthesis and then I take, actually, let's see, I observe there's a B on the left-hand side of both terms. And I see that I have a C transpose A inverse on the right-hand side. And so I can take them outside, I can factorize them. So here's what I have. I took B common here, then I have 1 plus, here I have a 1 right here because I have taken C transpose A inverse outside on this side too. So I have a 1 here plus, what do I have here? Once I remove the B and the C transpose A inverse, you have C transpose A inverse B. This. Okay. And why do I have a 1 here? Because I know that C transpose A inverse B is a scalar. Be careful, okay, when you're doing the factorization. If this would have been a matrix, you would have put an I here, an identity matrix here when you're doing the factorization. Anyway, and in the denominator, you have this. Now, knowing that what's in the numerator, this parenthesis is a scalar, I can take it outside. Never change the order of appearances of the vectors and matrices in a product, except it's a scalar. If it's a scalar, then you can put it anywhere you like. Okay, so that's what I do next. So I take it to the left. You had a question?
So how we actually consider that one that in factorization of the matrix we need to put I identity or 1, because in factorization you have put 1 which is scalar.
Yeah. So how do we know that? Because C transpose is a 1 by n. Okay, so let me use the, how do I do this? So A transpose, what was it? C transpose A inverse B. C transpose A inverse B. Okay, now this is a 1 by n matrix vector. C transpose. This is n by n, and this is n by 1. Now the inner dimensions, when you do a product, the inner dimensions must match. These two match. A inverse, these two match. And the product will be the outer dimensions. Okay, so 1 and 1, scalar. So this will be a 1 by 1 matrix, which is a scalar. Okay, now suppose, just to give you a little more insight, suppose I just had this, C transpose A. This would be 1 by, n by, 1 by n. And this would be n by n. This would give you the inner dimensions match, and so this would be a 1 by n row vector, this product. Suppose I had A, B. I have A, B. This is n by n, this is n by 1. Inner dimensions match, I'll get the product will be a column vector, n by 1 column vector. Okay, so now since this is a scalar, I took it outside. Now what do you see? Numerator and denominator. They are equal. And so the thing is, you got to observe the denominator. We have to cancel the denominator, right? somehow we should get, this term should be equal to negative of BC transpose A inverse. Okay, that's what this term should be. So you need to have a little bit of insight here. Okay, so I'm trying to make this term equal to negative BC transpose inverse so that these two will cancel out and I'm left with the identity matrix. Okay, and that's why I chose to factorize B on this side, take B common on this side and C transpose A inverse on this side so that I'd be left with something, a scalar, which would be equal to the denominator. Okay, and so, anyway, so what's the next step? We can cancel out the numerator and the denominator, they're both scalars. So, what do I get? This side will be BC transpose A inverse with a negative sign here. So, I plus BC transpose A inverse, negative BC transpose A inverse, I get the identity matrix. So, we have proved the Sherman-Morrison formula. Now, wrong approach. Okay, and be very, very careful in your homework because these are places where I take off a lot of points. Basically, if you don't know elementary matrix operations, that's a big no-no in this course. So suppose you do it like this. I take BC transpose A inverse out common on both sides. Okay, now, and you write a 1 here. First of all, numerator and denominators are not the same, but now this 1, is it correct? Is this a scalar, a vector, or a matrix?
It's a matrix.
It's a vector. It's a column vector.
Oh.
B, C, wait, n by 1, 1 by n. Oh, no, it's an n by n matrix. Exactly. This side is a matrix. I'm sorry. So this is a matrix. You cannot have a 1 here. This is wrong.
Even the factorization is wrong because we need to look for the order that C transpose.
No, I've preserved the order here. I've preserved the order here.
Okay, okay.
Okay. Cannot factorize as 1 is a scalar, but BC transpose A inverse is a matrix. We could have done it this way. This would have been a correct step, but it wouldn't have gone anywhere because then what do? Right? You're stuck with this. This is not equal to the denominator. How do we somehow cancel out the numerator and the denominator? So you have to apply some insights when you're doing these kind of derivations. So it leads to nowhere as we cannot simplify any further. We have reached a dead end. Okay. Vector norms. Now this is a vector x and its scalar elements or scalar components are x1 until xn. This is a standard representation of a vector. The LP norm of a vector is defined as we take all the scalar elements, take the absolute values and raise to the power of p, x1 to the power of p plus x2 to the power of p until xn to the power of p, and then we take the pth root of that. That's the LP norm of the vector. And it, in a way, it's kind of like the length of the vector. When p equals 1, so we just add up the absolute values of the elements. Infinite norm, when you take limit p equals infinite in this expression, then what will happen is when you're raising everything to the power of infinite, limit everything approaches infinite, the biggest one, x1, x2, x3, the one which has the highest value will stand out because you're raising everything to such a high exponent, right, to the power of p. P approaches infinite. So only the largest one will dominate. And then you are again reducing it. We are taking the pth root of that. Okay, and so that will give you whichever one is the highest, that one will dominate here. And so the infinite norm is the maximum of x1 absolute value, x2 absolute value, until xn absolute value. There's an example. And x2 norm is the standard norm. So if this p doesn't appear in the subscript, then by default, it's the L2 norm or the Euclidean norm, which is this. That's our default norm, and that's square root of x transpose x. If you take x transpose here, it'll be a row vector and multiply it with x. That's what you'll get. x1 square plus x2 square plus x3 square, everything, and the square root of that. Because it's 2 norm, so we have 1 over 2, that's square root. Okay, yeah.
It's in a project, right? X transpose.
Inner product, yes.
Yes, so my question is, like in LP norm, we actually consider it as the length of a vector.
Yeah.
So if we see in 2 dimension or 3 dimension based on the element, it's a length. So why there are so many definitions, but the length is absolute thing?
No. In only one special vector space is it absolute. As long as the LP norms obey certain things, they have to be greater than equal to 0, they have to obey the triangle inequality and so on, then its length is valid. It's a valid measure of length. So length is something more general than what you're used to. The reason we use L2 norm, the Euclidean norm, is because it's differentiable to begin with. You'll see all that later. It's more mathematically tractable, that's why. Okay, so the LP norm is always greater than equal to 0. And then we multiply, so this is something that any norm should obey, this rule. LP norm of alpha times x. So if you scale x by a factor alpha, then the LP norm also increases by that factor alpha. Triangle inequality. X plus y, the LP norm of x plus y should be less than the LP norm of x plus the LP norm of y. And all of these measures will obey this triangle inequality. Okay, so that these are all unit circles. This red diamond, the blue square, they're all unit circles depending on how we define the norm. Okay, so this green circle is what's the radius of this? So every point on this green circle is at a distance of 1 from the origin using L2 norms. The L2 norm, if you take any vector from the origin and connect anything in the circumference here, then the length of L2 norm of that vector would be equal to 1. Okay, now why is the L1 norm like this? Remember, the L1 norm, what do? You take well, it's 2 dimensions, so you have 2 elements in the vector. You add the absolute values, right? So here, well, this makes sense. This vector is 0, 1. This vector from here to this point is 1, 0. X is 1, x1 is 1, and x2 is 0, right? If you take a vector from this origin to this point here. That will be 1, 0. And add 1 plus 0, you'll get 1. So the length would be 1 in terms of the L1 norm. Now what about something here? Suppose I connect this point to this point. This vector will be x1 is half, x2 is half. Half plus half is 1. Correct? And so the distance from here to here in terms of the L1 norm is also 1. So every point here in this red diamond has a L1 norm of 1. So it, in fact, is a quote-unquote circle. Okay. Now let's look at the infinite norm here. Okay, this point here is, this point here, observe my cursor, okay? It's 0, 1. No, it's 1, 0. X1 is 1, X2 is 0, right? So the L infinite norm is take the maximum, absolute value of the maximum, 1. Likewise, this point is 0, 1. Take the maximum, 1. Negative 1, 0. Take the absolute value of the maximum, 1. So these 4 points are taken care of, these 4 corners of the, no, these 4 points in this blue square. What about this point? What are the coordinates of this point?
1, 1.
1, 1. So a vector from the origin to this point here, this corner would be 1, 1.
Maximum.
And the maximum is again 1. So the L infinite norm of that vector would still be 1. So in fact, all these points in this blue square have the same L infinite norm of 1. They are at the same unit distance from the origin. Okay. So this is another alternate notation for the inner product. I shall barely use it, but it's good to be familiar with it. Okay, and inner product is a little more general, but for our purpose, this is the inner product, X transpose Y, which is the same as Y transpose X. Okay, X transpose Y equals Y transpose X. Now, in physics, what we've seen is the inner product is, we've used the dot product, right? And that's equal to the L2 norm here. The length of X and length of Y, I'm using the Euclidean norm because I don't specify P and, as subscripts, okay? Times cosine of the angle between them, right? That's the inner product. Okay, that's the angle between them, X and Y. We're looking at 2 dimensions or 3 dimensions. And so take the cosine of the angle between them and the product of their lengths, and so you get the inner product. Projection of X onto Y. Now, what I'm interested in is this. So this is X, this is Y. I want to know, this is if I draw an orthogonal line from Y to this X. So this length of this line is the projection, the magnitude of the projection. Okay, and how do we get that? See, X transpose Y gives you this. This will be, if you use geometry, this will be X cosine theta, right? Length of X times cosine theta is the length of this, right? And so all you have to do is take this, the inner product, and divide it by the length of Y, right? And so this is the projection of X onto Y. Cauchy's-Schwarz inequality. The norm of X transpose Y is less than equal to the norm of X times the norm of Y. Why? Because you have the cosine theta, which is between 0 and 1. Any questions? Well, now observe this is a scalar, X transpose Y. The norm is just the absolute value. Yeah.
So in the projection of X onto Y, if we actually put the value of X transpose Y equal to XY cos theta, then this Y can be cancelled from numerator to denominator. Y can.
Yeah, that's
then
what.
it become only X cos theta.
Yeah.
So this is actually the geometry that whenever we need to see the projection of the vector on the x-axis, we simply multiply with the cos theta.
Yeah.
And for y-axis, we simply multiply with sin theta.
Well, let's not get into sine theta or anything. Just we'll avoid geometry here. But so that would be, if you want to take the projection of y onto x, then you have to divide this with x, length of x. Okay. Okay. Now matrices have norms too. You can define a matrix norm. So this is the induced norm of a matrix. So why we call this an induced norm? Some matrix norms are induced norms. So that's because the definition of the matrix norm is induced. It comes from the definition of the vector norm. Okay. So this is a matrix A, and we want its LP norm. What we do is AX is a vector. Now, we will consider all x's of which are unit vectors in terms of the LP norm. So the LP norm of this x equals 1. Okay, so we'll consider all possible such unit vectors, and we'll then try to maximize this. So whenever we get the maximum, we keep tweaking x. As long as it's a unit vector, we keep tweaking x, and so at some point we'll get the maximum. And that's the LP norm of the matrix. Now, instead of constraining x to unit vectors, we can simply do max with respect to x of this divided by the LP norm of AX divided by the LP norm of x. Okay, this maximize this with respect to x, and that yields the LP norm of the matrix. Properties are very similar to properties of vector norms. LP norm of a matrix is always greater than or equal to 0. And it's the same thing with matrices. When you scale up the entire matrix by a scalar alpha, then the LP norm gets multiplied by absolute value of alpha. LP norm of AB, the product of two matrices, is less than or equal to LP norm of A times the LP norm of B. And the triangle inequality also holds. LP norm of A plus B is less than LP norm of A plus LP norm of B. Holder inequality is, this actually holds for vectors too, but L2 norm of A is less than or equal to L1 norm of A times the L infinite norm of A. Now, let's, if you actually do the math, you can try to see it yourselves why it happens. Okay, from the definition. So, L1 norm, what we are doing here is with all the absolute values of the elements we consider, and we sum it over a row. Okay, so row sum, and then you take the maximum. So all the row sums you get, and then you take the maximum of that, and that is the L1 norm. I'll give you an example. L infinite norm is just the reverse. You sum over all the columns and then look at the sums, whichever is the highest. Here's an example. A L1 norm is, what do I do? Here I'm I'm summing over the columns, right? So 2, 1, and 2. I have to take the absolute values. Then 4, 2, and 1. 3, 3, and 1. And then this gives me 7. L infinite norm is, now I do the addition row wise, 2, 4, 3, then 1, 2, 3, 2, 1, 1, and that gives me 9. There's another norm that's called the Frobenius norm. Okay, and the Frobenius norm, AF. Here what I do is take all the elements, square them up, or if they're complex quantities, then take the absolute values and then square them up, take the squares and add all of them, rows and columns. So I'm basically treating it like a vector. Okay, and that is the Frobenius norm of the matrix. And we have this property for Frobenius norm. So let's look at the Frobenius norm of this matrix here, and I have intentionally placed complex quantities. So one, I have to take the absolute value and square of the absolute values, right? 1 and 1 plus j, what's the length of 1 plus j? That's square root of 2. Square of that is 2. So 1, 2, 4, 0, 1, and 1. 1, 2, 4, 0, 1, 1. Take the square root of that, that gives me 3. So that's the Frobenius norm. A Hermitian is this. This is A, and then what I've done is I've flipped the rows and columns, and I've taken the complex conjugates. And I get this is A Hermitian of A, and then when I multiply them together, I get this. Okay. Trace of this is 7 plus 2, sum of the diagonal elements. That's 9. Square root of 9 is 3. Right? And so you'll get 3 again. So this verifies this expression here. Block matrices. Now, this is something that you might not have dealt with, block matrices. So this is a block matrix. These are all block matrices. All these elements inside are matrices. The dimensions must match. The number of columns of A and the number of columns of C must be the same. The number of columns of number of rows of C must be equal to the number of rows of this I. Well, this is an identity matrix, so it's a square matrix. And the number of columns of the 0 must be equal to the number of columns of this I. In fact, they're all of equal size. But that's not necessarily the case. So we have to prove this. The good news about block matrices is, as long as you preserve matrix operations, you can treat these as regular matrices. Okay, so let's prove this as a demonstration of how to handle block matrices. So we have to prove this. So let's go ahead and proceed with the left-hand side. Left-hand side is this. Then I multiply AI plus 0, then A inverse B plus 0 times this. So A inverse B plus 0. Then next row we'll have C times I plus I times 0, that's 0. CI plus 0. Then C A inverse B plus I times D minus C A inverse B. What's C A inverse B? This guy here. What's I times D minus C A inverse B? I'm multiplying with an identity matrix, so I'll get the matrix itself. I'll get D minus C A inverse B itself. So this is D minus C A inverse B. And then AI plus 0 is A. This is A inverse is the identity matrix. We are left with B. Ignore the 0. We get B here. CI plus 0 is C. And here we have CA inverse B, and then negative CA inverse B. So we are left with D. Okay? Sorry, this was a redundant slide. I forgot to delete it. Anyway, so gradient. Now we'll do a little calculus. Gradient of a multivariate function. What's a multivariate function? Its argument is n dimensions. So it takes a vector as an argument, but it maps it to a scalar. Like LP norm is such a function. So the definition of the gradient is this. Del f of x equals, these are both valid notations, equals partial f over partial x1, partial f over partial x2 until partial f over partial xn. I basically take each element of x and differentiate this, find the derivative with respect to each of those x's, and then stack them up as a column. That's the gradient. Hessian of a multivariate function. The Hessian is this. It's equivalent to the second derivative, and the Hessian is a matrix. Furthermore, the Hessian is a symmetric matrix. It's this definition here. I take all the second derivatives, partial square f over partial x1 square. Look at the diagonal elements. I have x1 square, x2 square, xn square. I'm taking the second derivatives with respect to x1, x2, x3, and so on. Here, I'm differentiating with respect to x1, then x2. Here, I'm differentiating with respect to x2, then x1, and so on. But we know that the order of differentiation doesn't matter. That's why this will be equal to this will be equal to this, and so forth. And that's the reason we get a symmetric matrix. So this is the Hessian of a multivariate function. We'll be using the Hessian and the gradient a lot in the second half of this course. Quadratic form. So here is a multivariate function. It's a it's a multivariate function, and it's a quadratic function. You know what a quadratic function is in terms of scalars. So here this is the quadratic term, and this is a scalar term. And so this is a scalar. This is a scalar. This is a linear term. Excuse me, I don't mean scalar term. This is a quadratic term, and this is the linear term of this function. Okay, and this is the matrix Q. It has to be a square matrix, X transpose QX. Half of X transpose QX plus P transpose X is this function here. And in terms of the scalar components, this is what you would arrive at. The gradient of this, now this is very important for you guys to understand, is half Q plus Q transpose X. So this is the derivative of the first term here of this function, half Q plus Q transpose X, and the derivative of the second term, P transpose X, is P. Okay, remember, P transpose X is the same as X transpose P. Okay, why? Because P transpose X is a scalar. Transpose of a scalar is equal to the scalar itself. So if you transpose the scalar, it won't make any difference. So take the transpose of P transpose X, what's X transpose P. So derivative of X transpose P will be equal to P. Derivative of P transpose X will be equal to P. Remember, when we have P transpose X, this transpose here disappears. Okay, we are always dealing with column vectors. The gradient is a column vector. So this is the expression for the gradient. And I think there's an example in the next slide. And this is the Hessian. Second derivative is a matrix. It's half Q plus Q transpose. And this is something you have to remember. Now, what happens when Q is symmetric? Then the expressions for the gradient and Hessian become a little easier, right? Q plus Q transpose, Q equals Q transpose. So I can replace this with twice of Q, and then half and 2 cancel out. So it'll be QX. And the Hessian would simply be Q in that case, right? So del f of x is QX plus P, simple, when Q is symmetric, and the Hessian is simply Q. Okay? Here's an example. This is f of x. Okay, this is my matrix Q. 2, 1, 1, 3. It's symmetric. And this is my 3, negative 1. It's remember, I have to take transpose here, right? So P is a column vector, so P transpose is this 3, negative 1, this row vector. And when I simplify this, I get this expression here. So this quadratic term here gives me all these, the first 3 terms, which are quadratic. It involves x1 square or x2 square or x1, x2. And this linear term here gives me thrice x1 negative x2. And that, we can express that as in this form, vector form. The derivative, if you look at this expression, the derivative is, you can just differentiate this with respect to x1 and x2, and you get this and this. And you can verify that that's also the same as, this is q, right? Q x plus p. Agreed? Oops. And the second derivative is, you can take the second derivatives and place them all here. You'll get 2, 1, 1, 3, and that's equal to q. Just for your information, every time we're dealing with a quadratic, 99.9% of the time, this has to be a symmetric matrix. Okay, so any questions with the course material so far? I know I went very fast, and I assumed that you guys know everything about basic matrix operations. I call it a review, but in reality, you learned quite a bit. You were exposed to new things. But these 2 lectures that I said, the first 2 lectures, I'll go at express speed. Yeah.
Block matrices will be deal in the same way like we deal the simple matrices.
Yes.
All the rules of matrices will apply on the block matrices.
Yes. Including determinants. You look at that. You'll see that. Now, for instance, what's the determinant of this? If they were scalars, the determinant of this, only look at this first matrix, okay? A0, C1, it would scalars, A0, C1. The determinant of this is A, or absolute value of A, right? Now, they're matrices. What's the determinant of this matrix? Determinant of A. Okay. What's the determinant of this matrix? It's determinant of only this, D minus C A inverse B. Like that. Okay? So with this, we end today's lecture, unless you have, I'm sure you have questions, so feel free to ask questions. One hidden purpose of this course is so that once you go through this course, and if you look at all the IEEE transaction papers, right, controls, communications, AI, machine learning, anything, you'll see there are a lot of operations like this. After this course, my hidden purpose is you'll be familiar with the definitions. And you'll be able to follow technical research papers. That's a big thing about this course. Okay, so unless there are any other questions, how do I